The sigma notation or the summation notation plays an important role in calculus, especially in definite integrals. So the Greek letter sigma is used to denote a sum of a finite or an infinite number of terms. So we define the summation of f of I from m to n, as the sum of f of m plus 1 plus f of m plus 2 plus and so on and so forth plus f of n minus 1 plus f of n. Alright? So the right side is the expanded form of the sum. This is the expanded form. And the left side is the compact form of the sum that uses the sigma notation. Alright, I is the index of summation. I is the index of summation. M is the lower limit of summation. And n is the upper limit. What we do is we simply substitute the integers m plus 1, up to n, to the index I. I is sometimes referred to as the running I because it runs from m to n. Now, the index of summation I is sometimes referred to also as a dummy variable. It's a dummy variable. Why? Because we can replace the index I by any other variable and it will not change the sum. So the sum of f of I from m to n can be written as the sum of f of j from m to n, or the summation of f of k from m to n. So replacing the index I by some other letter will not change the variable. So let us have some examples. The summation of I squared, I from 1 to 10. In the expanded form, this is simply 1 squared, so the lower limit is 1. We replace I by 1 and then squared, plus the next integer after 1 is 2 squared, then 3 squared, until the upper limit 10 squared. So that will be equal to 1 plus 4 plus 9 plus and so on and so forth plus 100. And then you just evaluate this sum. Next, the sum of 1 over I from 10 to 20. The lower limit starts at 10, so I becomes 10. So 1 over 10 plus the next integer after 10 is 11. So 1 over 11 plus 1 over 12 and so on and so forth plus 1 over the upper limit, which is 20. Next, the summation of the quantity 2i plus 1 squared, I from 1 to 5. So same thing, we replace I by the integers 1, 2, until 5. So that will be 2 times 1 plus 1 squared plus 2 times 2 plus 1 squared plus 2 times 3 plus 1 squared plus 2 times 4 plus 1 squared, and finally 2 times 5 plus 1 squared. So that will be 2 times 1 plus 1 is 3 squared is 9, 4 plus 1 is 5 squared is 25. 6 plus 1 is 7 squared is 49. 8 plus 1 is 9 squared, 81. Plus 2 times 5 is 10 plus 1 is 11 squared is 121. Next, the summation of negative 1 raised to I over I plus 1, I from 1 to 15. So, negative 1 raised to 1, I is 1 over I plus 1, or 1 plus 1. Then, negative 1 raised to 2, 2 over 2 plus 1, plus negative 1 raised to 3, 3 over 3 plus 1, and so on and so forth, plus negative 1 raised to, the upper limit is 15, 15 over 15 plus 1. So negative 1 raised to 1 is negative 1 over 2. Negative 1 squared is positive 2 over 3. Negative 1 cubed is negative 3 over 4. And then we continue until the last term, negative 1 raised to 15 is negative 15 over 16. Okay? Let us have another one. Say the summation of x sub I from 1 to infinity. It is the index I that we are going to replace by the integers 1, 2, and so on and so forth. So, the expanded form of this sum will be x sub 1 plus x sub 2. I is the subscript, no? So that is the one that we are replacing by the integers 1 up to infinity, plus x sub 3 plus, and so on and so forth. No? So this will be an ending because the upper limit is infinity. Similarly, if we have the summation of f of x sub I delta i's x I from 1 to infinity, in the expanded form it will become f of x sub 1 delta 1x plus f of x sub 2 delta sub 2x plus f of x sub 3 delta sub 3x plus, and so on and so forth. Okay? For the next set of examples, we will be given the expanded form and we will write the corresponding sigma notation. Okay, so we write the following sums using sigma notation. So we try to figure out what will be the corresponding sigma notation for the following sum. So let us start with, say, the sum 2 plus 5 plus 10 plus 17 plus 26 plus, and so on and so forth, plus 101. So at first glance, it seems that there is no pattern for this series of numbers. But if we are going to write each as a sum, say 1 plus 1, 5 is 4 plus 1, 10 is 9 plus 1, 17 is 16 plus 1, 26 is 25 plus 1, until 100 plus 1. And what do we see here? We see a constant addend of 1, right? And also, the remaining integers 1, 4, 9, 16, 25, and 100 are perfect squares. So, This is actually the sum of I squared, no? 149 up to 100, that is I squared, plus the constant addend of 1. Quantity I from 1 up to what we have here is 100, which is a perfect square of 10. So I is from 1 up to 10. Alright? By the way, for the next example, negative pi plus pi minus pi plus and so on and so forth plus pi, and that is 100 times. Okay, what do we see here? In one of the examples we had a while ago, we have alternate positive and negative terms. No? In one of the examples, notice that we'll be generating alternate negative and positive terms if we have the factor negative 1 raised to some power I, right? So that will be, if I starts at 1, that will be negative 1 raised to 1, then negative 1 raised to 2, negative 1 raised to 3, and so on and so forth. So it will be alternately negative and positive terms. So for number 2, as you can see, it's an alternate, uh, uh, the alternate terms are positive and negative with a constant pi. So this means that the equivalent sigma notation for this will be the summation of negative 1 raised to, the first term is negative, so it should be I raised to, or I equal to 1. No? Negative 1 raised to I, where I is 1, will give us a negative term. And then the constant term is pi. And it says that it runs from, or I runs from 1 up to 100 because there are 100 copies of pi, but alternately negative and positive. If the first term is positive, if the first term is positive pi, the negative pi, and so on and so forth, pi minus pi. So this will be the last two terms, the first two terms and the last two terms. So it will be negative 1 raised to, if it is the sum starting, I starting at 1, the exponent of negative 1 could not be 1 or I, no? Because it will be negative. So in this case, the exponent will be I plus 1 for the first term to be positive. That is when I starts at 1. Okay? So if I starts at 1, negative 1 raised to 1 plus 1 is 2, or negative 1 raised to 2 is positive, that will be the sign of the first term. Okay, so let us go to example number 3. Say we have 2 plus 4 plus 6 plus, and so on and so forth, plus 200. What do we see here? We see a sequence of positive even integers. And even integers can be written in the form 2n. So in this case, our index is I, so it will be 2i. The sum of 2i, where I starts at 1, up to the last term is 200. So that means that if 2i is 200, your I there is 100. So the upper limit is 100. Okay, so another one, 1 plus 8 plus 27 plus 64 plus, and so on and so forth, plus 1000. What are these integers? 1, 8, 27, 64, and 1000. You should know that these are perfect cubes. No? That will be 1 cube plus 2 cube plus 3 cube plus 4 cube plus and so on and so forth plus 10 cube. So we shall write this sum as the summation of I cube, I from 1 up to 10. Okay? Let us take on the next one. 2 plus 6 plus 12 plus 20 plus and so on and so forth plus 990. Again, at a glance, you cannot see the pattern. So, let us express this as products. No? So, 2 is 1 times 2, 6 is 2 times 3, 12 is 3 times 4. Okay, so for the first three terms, you notice that the first factor, the first the first integer of the three factors are 1, 2, and 3. So it's a sequence, no? So it's a sequence 1, 2, and 3. And then the second factor is 2, 3, and 4. So 20 is 4 times 5, no? Following this pattern. 1 times 2, 2 times 3, 2 times 4, 4 times 5. And that's correct, no? 4 times 5 is 20. And then for the last term, 990, then that will be equal to what? 9 times, or 99 times 199 times 100. Okay, so it's supposed to be, the last term is supposed to be 99,000. Okay, so it should be 99 times 100. Okay, so we shall write this now as the sum of I times 2 is the next integer after 1, 3 is the next integer after 2. So if the first integer is I, then the second integer will be I plus 1. Okay, and I is from 1 to 99. Okay, let us have one final example. Okay. 2 plus 4 plus 8 plus 16 plus and so on and so forth plus 10, 24. So what are these? These are actually powers of 2. So 2 raised to 1 is 2, 2 squared is 4, 2 cubed is 8, 2 raised to 4 is 16, and 1024 is actually 2 raised to 10. So we shall write this as the sum of 2 raised to I from 1 up to 10. Alright? So let us now go to the different properties. Properties of summation. The first one is the sum of the constant C, I1 to n, and that is equal to C times n. What is the proof of that? When you say the sum of C, I from 1 to n, it is equivalent to the sum of C added to itself n times. Okay? So for I equal to 1, it will be C, even in the absence of the index, in the summand. No? This is the summand. The summand is simply C. There is no index involved in the summand. So even in the absence of the index I, we add C to itself, beginning at I equal to 1 up to n. So for I equal to 1, it is C, plus for I equal to 2, plus C, plus for I equal to 3, C, and so on and so forth, up to I equal to n. So, example of this is the summation of 3, I from 1 to 100 is simply 100 or 3 times 100. No? 3 times 100 equal to 300. Next is the summation of k f of I from m to n, is equal to k times the sum of f of I from m to n. So, for example, if we want to find the sum of 4i from 15 to 100, that is the same as 4 times the sum of I from 15 to 100. So in other words, we can bring out the constant. No? We can write the constant before the sigma. Next, the summation of the sum of f of I, or the difference, f of I minus g of I, quantity I from m to n, is equal to the sum of f of I from m to n, plus minus the sum of g of I from m to n. So as an example, if you want to find the sum of 4 plus I squared, I from m to n, that will be equivalent to the sum of 4 plus the sum of I squared, both sums from I equal to m up to n. Alright? So in other words, you can distribute the summation or the sigma. Next, the sum of f of I from m to n, can be written as the sum of f of I from 1 up to n, minus the sum of f of I from 1 up to m minus 1. So, if you want to find the sum of I from 31 up to 100, that will be equivalent in finding the sum or the difference of the sum of I from 1 to 100 minus the sum of I from 1 to 30. Okay? So if you want to find the sum from 31 to 100, take the sum from 1 to 100 but subtract the sum from 1 to 30. Next, the sum of f of I minus f of I minus 1, I from 1 to n, is equal to f of n minus f of 0. Okay, so in here, instead of expanding the sum, it will give you immediately the result by getting the difference f of n minus f of 0. So, f of n is obtained by simply substituting the upper limit n to I. Here is your f of I. You just replace I by n. So, if you want to find the sum of f of I minus f of I minus 1, I from 1 to 30, that is simply f of 30 minus f of 0. Okay, so here's another example. You want to find the sum of 2 raised to or rather, sum of 2 to the I minus 2 to the I minus 1. Alright, I from 1 to 40. Your f of I here is 2 raised to I. And f of I minus 1 is 2 raised to I minus 1. So, here it is. This is your f of I, while this one is your f of I minus 1. So, you simply get f of n or f of 40. So, replace I by 40, that will be 2 raised to 40. And then f of 0, that will be 2 raised to 0 or 1. So, immediately we find that this is equivalent to 2 raised to 40 minus 1. Okay, without expanding the sigma. Here's another example. So you want to find the sum of 1 over n minus 1 over n plus 1. I is from 1 to 100. Okay? So what is my f? Okay, I should write here 1 over I. My index is I. So 1 over I minus 1 over I plus 1. Okay, my f of I is 1 over I, and my f of I minus 1 should be 1 over I minus 1. But it seems that there is a difference, no? It is not 1 over I minus 1, but 1 over I plus 1. We take note that I plus 1 is greater than I, right? So, what we will do here is we will rewrite this as the sum of the negative of 1 over I plus 1 minus 1 over I from 1 to 100. Okay? And then I can factor the negative sign. So negative times the sum of 1 over I plus 1 minus 1 over I. So we shall now identify our f of I, which is 1 over I plus 1, and f of I minus 1 is 1 over I minus 1 plus 1, or 1 over I. Okay? So that will be correct. 1 over I will be your f of I minus 1, while 1 over I plus 1 is your f of I. Alright? That is your f of I. I is from 1 to 100. So we solve for f of 100. That will be 1 over 100 plus 1, or 101. And f of 0, no, replace I by 0, 1 over 0 plus 1, or 1. So this now becomes the negative of 1 over 101, okay, minus 1. So 1 over 101 minus 1 is 1 minus 100, 1. So negative 100 and negative, that will be positive 100 over 101. Okay? This is negative 1 minus 101 over 101. Okay? So we go to some important formulas involving sigma. The first one is the summation of I from 1 up to n. Let me write it nicely. Okay, I. It is equal to 1/2 of n times n plus 1, or n times n plus 1 all over 2. The other formulas are summation of I squared, I from 1 up to n will be equal to n times n plus 1 over 2n plus 1 all over 6. Next, the sum of I cubed, I from 1 to n will be n squared times n plus 1 squared all over 4. Another is the sum of I to the fourth, I from 1 to n will be equal to n times n plus 1 times 6n cubed plus 9n squared plus n minus 1 all over 30. Now, you can also write this as n times n plus 1 times 2n plus 1 plus 3n squared plus 3n minus 1 all over 30. Okay? So, let me show you the proof of the first one. So, it says that the sum of I is equal to n times n plus 1 all over 2 I from 1 to n. Okay. So let me write I in the expanded form. 1 plus 2 plus 3 plus and so on and so forth plus n minus 2, n minus 1, n. So the first three and the last three terms. I am going to write again the sum of I from 1 to n, but in the reverse order. So that will be n plus n minus 1 plus n minus 2 plus the last three terms, 3 plus 2 plus 1. And then I'm going to add these two. Okay. The sum of I and the sum of I is, of course, 2 times the sum of I. I is from 1 to n. We add term by term, so that will be n plus 1. Next, 2 and n minus 1, that will give me what? N minus 1 plus 2 is, again, n plus 1. The third term, 3 and n minus 2. N minus 2 plus 3 is, again, n plus 1. And so on and so forth. Down to the last 3. N minus 2 plus 3 is also n plus 1. Plus n minus 1 plus 2 is also n plus 1. And finally, n plus 1. So n plus 1 is common to all terms, and there are n copies. No? So there are n copies. So it's simply n times n plus 1. And of course, if you want to find the sum of I from 1 to n, you divide both sides by 2. So divide both sides by 2 will give us n plus 1 all over 2. Okay? Now, the other three can also be proved using, what you call this? I almost forgot. Mathematical induction. Yes. You can prove the other three formulas using mathematical induction. Actually, one can also be proved by mathematical induction. Okay, so let us have some examples. Let us find the sum of I times I plus 3, I from 1 to 20. Okay. So first, let us write the summand as I squared plus 3i. I from 1 to 20. And we know that this can be written as the sum of two sigma or two summations. The summation of I squared, I from 1 to 20, plus the summation of 3i, I from 1 to 20. Okay, what is our formula for the summation of I squared? It will be n times n plus 1 times 2n plus 1 all over 6 plus 3 is a constant and the sum of I is n plus 1 over 2. Alright, so what is our n? Our n is 20. So 20 times 20 plus 1 or 21 times 2 times 20 plus 1, that will be 41 over 6. Okay, and then we have 3 times n is 20 times 20 plus 1 is 21 all over 2. And that should give us 3,500. Okay? Another example. Say you want to find the sum of all even integers less than equal to 200. Okay, so let us find the sum of all even integers. So that will be 2 plus 4 plus 6 plus up to 200. Of course, we can do it manually, but there is an available formula for this. Now, these even integers can be written as 2i. Every even integer, or the set of all even integers, can be written in the form 2i. So we are actually getting the sum of 2i, I from 1 to 100. Because the last term is 200, so your upper limit is 100. 100 times 2 is 200. So that is equivalent to 2 times the sum of I, which is n plus 1 all over 2. So 2 will cancel. That will be 100 times 101. So that will be 10,100. Okay? So 100 times 100 is 10,000 plus 100 is 10,100. Let us find the sum of I squared, I from 11 to 30. Okay? You see that the lower limit is no longer 1 but 11. And we know that we can write this as the sum of I squared, I from 1 to 30, minus the sum of I squared, I from 1 to 11 minus 1, that will be 10. So we subtract 1 to 10 from 1 to 30. And that will give you the sum from 11 to 30. Then we apply the formula for I squared. That will be n times, or rather n squared times n plus 1 squared all over 4. But your n here is 30. Alright? Then minus n squared, n plus 1 squared all over 4. But n is 10. Okay? So, what do we have here? 30 squared times 30 plus 1 is 31 squared minus 10 squared times 10 plus 1 is 11 squared all over 4. And that should give us 213,200. Okay? So you work on the following exercises. You work on the following exercises. For letter A, we write the first 4 terms. So the summation of 2i, excuse me, over 2i plus 1, I from 4 to 20. Then the summation of negative 1 raised to I, x sub I plus 2, I from 1 to infinity. Next, the summation of I minus 1 over I plus 1, I from 10 to 100. And the summation of I raised to I from 1 to 15. For the next set, you write in sigma notation negative 3/4 plus 3/4 minus 3/4 plus and so on and so forth 50 times. No? So 50 times. Next, 1 plus 9 plus, okay, I think I made a mistake here. Let me change this. 1, it should be 2. 2 plus 11, plus, let me see. Wait, 1 plus 9 plus 25 plus 49 plus 81 plus 121 until 121. Then 3/5 plus 5 over 7, 7 over 9, plus and so on and so forth, plus 21 over 23. Number 4, 5 minus 10 plus 15 minus 20 plus and so on and so forth, minus 500. And then letter C, evaluate the sum of summation of I plus 3 squared, I from 1 to 20, and the summation of I times 2I minus 1, I from 15 to 30. Okay?